Good day, everybody. We're talking about quadrilaterals, a particular kind of quadrilaterals today. So this is section 2.3 in the notes. And so we have two guys, Saccheri and Legendre, and they come up with quadrilaterals. And what are they trying to do? They're trying to push all the way through to proving that rectangles exist, right? With two pairs of parallel and congruent sides and four right angles, and they can't get there, right? So we're at the end of the 1700s, beginning of 1800s, I believe. No, wait, no, we're at the beginning of the 1700s, the end of the 1600s, beginning of the 1700s. And so they're trying to create these nearly rectangles figures, so that they can push through, and with just hopefully one or two more theorems, they can get there. All right. Well, we have some pictures of their attempt, and I've created these in GeoGebra. On the left, we have a Saccheri quadrilateral, correct? And what do we know? We know that these legs, they're called, these sides are congruent. The base here, segment AB, is the base. And what we'll try to prove, oh, and these are right angles, right? So we know that the base angles are right angles. So this is all we're given with a Saccheri quadrilateral. A Lambert quadrilateral over on the right is a quadrilateral with three right angles. And you're like, well, can't you prove that if there are three right angles, then the fourth one should be a right angle? And the answer is no, you can't. Not without a parallel postulate. So again, both Saccheri and Lambert were trying to create these nearly rectangles and then push through the idea that, that these um, rectangles do in fact exist. And the problem they were bumping up against is they don't in fact exist without the Euclidean parallel postulate or something equivalent to it to work with. Okay, so um, here are the theorems that we're going to prove. These are written in section 2.3. And the first few are just follow your nose proofs. And as we're going over these, I want to encourage a specific way of learning about these proofs. And it turns out that mathematicians rarely memorize a proof step by step. They have the idea of the proof in their mind, and they rely upon themselves to be able to fill in the gaps along the way in the moment, right? Um, and so one thing that I like to encourage my students to do is try to remember a proof outline. Try not to remember the whole proof, because it gets hard, right? If the proof has, 5 or 8 or 12 steps, memorizing them all is hard. Memorizing the two or three that are really important and allowing yourself to fill in the rest of the gaps is a lot easier. Okay, so I'm going to take that format as I look at these proofs. And the first one is the Saccheri diagonals are congruent. Okay, the diagonals of a Saccheri quadrilateral are congruent. Okay, well, it turns out that this is a very straightforward proof. All I'm going to do is construct the diagonals and follow my nose. Again, mathematicians call this a follow your nose proof. You just do the obvious thing. Okay, and let's talk about, what is the obvious thing. Okay, sorry, let me jump into, there we go. So we have ABC, an arbitrary Saccheri quadrilateral, and I've marked the legs congruent and the base angles congruent, and they're 90 degrees. Okay, so what's happening next? Okay, we're just noting that, what I just said, and then we're going to draw the diagonals. So we're going to construct AC and BD. Now, we're pointing out the fact that AB is congruent to itself. Why? Well, because we're going to use it as the base of both of these triangles. Okay, so we have the triangle on the left, which will have the base AB, will have the right angle, and we'll have the side AD, which is congruent to the side BC. So you can see, oh, if we use AB, the reflexive property of congruence, um, then we're going to be able to use side, excuse me, side angle side. I should have said side angle side congruence, right? Because I'm using AB, I'm using the two angles are congruent, and then I'm using that the legs are congruent in a Saccheri quadrilateral. Okay, and then what do we get? Well, because we have congruent triangles, we can use congruent parts of congruent triangles are congruent, and therefore we get the diagonals congruent like we were hoping to. So let me get rid of all of the drawing there. And what are we going to do? We're going to take a look. That's theorem 2.3.1. And we're also going to look at theorem 2. Okay, so what is that? Sorry. Let me advance the slide if I can. There we go. So the Saccheri summit angles are congruent. Okay, so we know that diagonals are congruent, and so we're going to use some triangle congruences again, and I think it will make sense once you see it. So let's jump back into this proof, right? Okay, so we're trying to prove that the summit angles are also congruent, but again, we're getting this, hey, this line DC, this line segment DC is congruent to itself by reflexivity. Okay, we still have that the legs of the Saccheri quadrilateral are congruent. And then we also have that the diagonals are congruent. We just proved that, right? And if you think about that, then we get triangle ADC is congruent to triangle BCD, right? So ADC is congruent to BCD. And yeah, the marks on the triangle are getting a little ugly, but yeah, that is side-side-side congruence. Sorry, let me. And now, because those triangles are congruent and because congruent parts of congruent triangles are also congruent, we get that ADC, angle ADC, is congruent to, or the measure of it is equal to the measure of angle BCD. That's what we wanted. Those were the summit angles. And for both of these proofs, we have that we started with an arbitrary Saccheri quadrilateral. So both of these results hold for all Saccheri quadrilaterals. Okay, so any Saccheri quadrilateral in neutral geometry, these two results will hold for them. Okay, so let's jump in and see what else we can prove here. And again, I'm adding some information for you on the slide, but I really do just use the outline, right? I'm trying to highlight what was important about this proof. And again, as soon as I'm reminding myself here to rely upon the fact that diagonals are congruent, the summit is congruent to itself, and side-side-side congruence. Honestly, the main thing I'm worried about is I need to know, hey, use side-side-side congruence, right? That there's some triangle congruence, and if you just look at it, you know what triangles you need to use because the triangles have to include the summit angles. Why? Well, because that's what I'm trying to prove. Those are the angles I'm trying to prove have the same measure. So step 3 there is the key step. All of this is good information for the outline. But get good at isolating what is in fact the key thing we need in this proof. And let's take a look at theorem 3. In a Saccheri quadrilateral, the summit angles are acute. Okay. So if you look back at section 2.2, theorem 16 is the Saccheri-Legendre theorem, and the angle sum of any triangle is less than or equal to 180 degrees. Okay, and then the corollary right after it is the angle sum of any convex quadrilateral is less than or equal to 360. Okay, well, So that's just a theorem. The theorem we're using is 2.2.17, right? That quadrilaterals have angle sums that are less than or equal to 360. And then from there, it's just do the math. Okay. Um, and if we just take a look here at the at the situation we find ourselves in, right? That, okay, if I have a right angle and I have a right angle, then I know that, right, the measure of angle A plus the measure of angle B plus the measure of angle D and the measure of angle C has to be less than or equal to 360. But these are both 90, right? So I end up with the sum of these two has to be less than or equal to 180, but we just proved that they're congruent. So I have a pair of angles that are congruent and whose sum is less than or equal to 180. What does that mean? Well, if we go back and look at the theorem, we've proven it, right? Um, the summit angles cannot be obtuse. They can be right, they can be acute, but they're both equal, right? And so they're both right or they're both acute angles. And this just follows directly from theorem 3.2.17. Okay. And now we're going to talk about the midpoint line of a Saccheri quadrilateral. Okay. Um, and we're going to have to use triangle congruence several times. Um, and you'll see why when we get it drawn out. But yeah, it's a bit of a tangled mess. It's pretty clear what we need to do, but it's a lot of bookkeeping to keep track of what we're actually doing. So the first thing you can see, we actually do have theorem 2.3.3 written out. I probably should have just shown you this rather than trying to do it in pen on the screen. But let's take a look at the second theorem here, 2.3.4, that the line joining the midpoints of the summit and the base of a Saccheri quadrilateral is perpendicular to both. Okay, so what are we looking at? We're looking at that red line. Okay, the red line RS. And what do? Well, it turns out that eventually we do all of these sort of subdiagonals. We'll see if we can get this one showing up. Okay, you can see the purple subdiagonals, you can see the green subdiagonals. What are we doing? We're creating triangles that we can solve, and then the triangle congruence will give us what we need. Okay, so what are we trying to prove? Well, let's look at this. We're trying to prove that these are right angles, that we have perpendicularity both where RS crosses the base AB and where it crosses the summit. Okay, so we construct RS given the midpoints of CD and AB, right? And then we construct these green line segments AR and BR. Why? Well, they're the ones we're going to need. And notice we have it listed right here. So ADR, right? So we're going ADR is congruent to BCR, right? BCR, and that is a correct congruence. But let's just make sure, right, that we have everything. Why do we have congruence? Well, R is the midpoint, so DR equals RC, right? We do know that the summit angles are congruent, right? And we know that the legs are congruent. So we turns out that we have side angle side, right? And so we get the congruence we initially want with side angle side. And now that we know that the green lines are congruent to each other. These subdiagonals are congruent to each other. And we know that S is the midpoint of AB, so AS equals SB. Let me draw 3 there. And we know that RS is congruent to itself by the reflexive property of congruence. So side, side, side tells me that ARS is congruent to BRS. Triangle ARS is congruent to BRS. And what do we have? We have two angles that are congruent to each other, but they're a linear pair. Okay, so we have this congruent linear pair, right? So we know that the measure of ASR plus the measure of BSR is equal to 180, but they're equal to each other. So I can just subtract one out. And then I know that I have an angle, let's say ASR is equal to 90 degrees, but it's also congruent to the angle BSR. So know that the measure of BSR is also 90 degrees. Okay, so the important, the absolutely vital feature here is that when we have a congruent linear pair, we have right angles, right? That's one of the most common ways we prove perpendicularity in Euclidean geometry is that we get a congruent linear pair and then we're done. There is a slight bit of algebra that you can do. And then we construct the purple ones. And I'm sorry that we've run out of most of the room here. I'll see if I can bring this up just enough so you can see it. We do the same thing. We do triangle congruence with SAS, and then we do triangle congruence with side, side, side. And we get a congruent linear pair up top, right? We get a congruent linear pair DRS and CRS. Same thing, that once I have the congruent linear pair, then I immediately get perpendicularity. So again, sorry that this proof got so big. That wasn't really my intention, but it happens. And again, the idea of congruent linear pair is how we're going to prove the triangle congruences. Okay, so let's jump back in. 4 theorems down now. Okay, and the PowerPoint slides also make the point about the congruent linear pair to prove perpendicularity. All right, so again, however you list your outline, and everybody will be slightly different, right? The congruent linear pairs is a key idea. Whomever you are, that's a key idea. All right, and moving forward. So the Saccheri base is parallel to its summit. Okay, and this is almost an absolute corollary to alternate interior angles. What is the alternate interior angles theorem? It says that if I have two lines cut by a transversal such that alternate interior angles are congruent, then the lines are parallel, right? And if you want to check this out, I'm trying to see where it is. Um, and I'm sorry, it's in 2.2. I am just struggling to find which theorem. 12, 2.2.12 is the alternate interior angle theorems. If two lines are intersected by a transversal such that a pair of alternate interior angles is congruent, then the lines are parallel. Okay, well, that's exactly the situation that we have when we look at the Saccheri quadrilateral, right? And so we have alternate interior angles congruent. Why? Because all 4 of the angles, DRS, CRS, ASR, and BSR are all right angles, all 4 of them. So pick any pair of alternate interior you like. And so we know that they're both perpendicular. RS is perpendicular to DC and is perpendicular to AB. And the corollary, 2.2.13, the corollary to alternate interior angles is that two lines perpendicular to the same line are parallel. So there you go. Just a straightforward result of AIA, alternate interior angles theorem, or the corollary to the alternate angles um, theorem 13 in section 2.2 just gives this to us. So I'm not going to belabor that proof very long. I'm just going to leave it there because theorem 2.2.13 is in fact pretty much the whole proof. Okay, so theorem 6, the Saccheri summit length is greater than or equal to the base length. And it turns out, jumping back into this picture, right, that the Saccheri quadrilateral, if I have that midpoint line, RS, the right side is a Lambert quadrilateral. And so is the left side. So it turns out that they're kind of mirror images, and you can prove that the right side of a Saccheri quadrilateral is congruent to the left side. But they're both Lambert quadrilaterals. Why is that important? Well, it turns out that when we go back, it's easier to prove theorem 8. What is theorem 8? Well, theorem 8 says that the summit of the Lambert is greater than in length than the base. Now I'm using those terms a little loosely just to give you the idea, but we're going to come back to this. Theorem 7 is another straightforward proof. The fourth angle is not obtuse. It's the same idea because the Saccheri Legendre theorem, which says triangles have angle sums less than or equal to 180, and the corollary to that, that quadrilaterals have an angle sum that is less than or equal to 360, and the Lambert quadrilaterals have three right angles, right? So, um, so yeah, if you make the equation, right, with angle W is equal to 90 degrees, and angle X is equal to 90 degrees, and angle Y is equal to 90 degrees, and then the sum of all four of them has to be less than or equal to 360, that leaves us with just this one, and we know that the measure of angle Z is to be less than or equal to 90 degrees. When we subtract out the 270 degrees to account for the measure of angle W plus the measure of angle X plus the measure of angle Y. We subtract that out of both sides. We're left with the equation you see on your screen. So again, this proof is not a hard one. And I don't even really know how to outline it. I've tried to do my best. But it really does just boil down to this, that we know that quadrilaterals have angle sums less than or equal to 360, and then just do the math. Okay, so to get these Lambert side lengths, the measure of the side included between two right angles of a Lambert quadrilateral is less than or equal to the measure of the side opposite it. Okay, let's look at these real quickly for a minute and just see. They're saying that any side that's included between two right angles is less than or equal to the length of the side opposite it, right? So this also can happen for the WX and YZ, but let's just look at this again, right? The measure of the side included between two right angles is less than or equal to the measure of the side opposite it. Okay. So again, it can apply this way. It can also apply, right? I have right angles at X and at W, so it can apply like this. That the measure of the distance between W and X is less than or equal to the measure of the distance between Z and Y. Okay, so either one of those is true. And by the way, I don't have to prove them both. I just need to prove one direction. Okay, but to do so, I'm going to start with what I call the Skew Saccheri lemma. And I just created this to help me prove theorem 8, okay? I made up the idea of a Skew Saccheri lemma. What is a Skew Saccheri quadrilateral? Skew Saccheri quadrilateral is one where the legs have different lengths. Okay, so the normal definition for a Saccheri quadrilateral is right angles. The base angles are right angles. And the legs are congruent. And then we end up being able to prove, therefore, that the summit angles are congruent. Okay. But this is going to be a slightly different situation with this Skew Saccheri figure where the legs are not, in fact, congruent. All right. So without loss of generality, assume that AB is greater than DC. So AB is greater than DC. Why? Well, we've said the legs aren't congruent, so that means that one leg is longer. Okay? And we could have done the right leg is longer than the left leg, but we did it the way we did it. And we're just saying, hey, the proof goes the exact same way if I did it the other side. Okay, now notice that we're going to extend the segment DC to the point P. And we're very specifically choosing the point P so that, and this says E instead of P, right? The problem here is that should be a P, that PC is equal to BA. Right? Why are we doing that? Well, now we have a Saccheri quadrilateral, and so BAP, the summit angles are congruent, so the measure of angle BAP is equal to the measure of angle CPA. And the angle at D is interior to angle CPA, also interior to BAP. And since it's interior to the measure of angle BAP, then we can apply the exterior angle theorem to ADP. Okay, so look at that triangle real quickly. ADP, right? So we're talking about this top triangle and applying the exterior angle theorem. We know that the measure of angle ADC is greater than the measure of APD. Know that the measure of angle ADC, right here, is more than this angle. Okay, well, angle P, because it was a Saccheri quadrilateral, was congruent to angle A. So there we have it, right? That the summit angle with larger measure is adjacent to the leg with shorter length, and here we have it. It is adjacent to DC. And so we're done. Okay, so you might want to rewind the video and watch that and follow that through more carefully. But it is true. It is true and it is proven. And now that it's proven, I can do this. And I'm trying to get as much space here as possible so you can see the whole proof. Okay, jumping back to the PowerPoint, let me just say, right, that we're going to use contradiction with cases. I don't know if you've ever done a contradiction with cases before, but it is a rather complicated setup. And you may not have seen it before. So let's go through it, knowing that we have the Skew Saccheri lemma to rely upon. Let's see if we can push this through. Okay, so notice where we start. We start with the trichotomy, and the trichotomy says that if I have two real numbers, x and y, right? If I have two real numbers, x and y, there's three relationships they can have. Either x is greater than y, or x is equal to y, or x is less than y, right? Those are the three possibilities. That's why it's called the trichotomy. Three things can be true about real numbers x and y. So notice that we start. So either leg AB is longer than DC, or it's equal to it, or it's less than it, okay? And we start with the first case. Okay, assume that AB is greater than DC. Well, what you'll notice is when we add in this orange line to show the assumption, this AD1 segment, we have the Skew Saccheri lemma set up, right? And we know that angle D is greater than, the measure of angle D is greater than the measure of angle A. But that's a contradiction. Why? Well, by theorem 7, right? If we have a Lambert quadrilateral with 3 right angles and D1, that angle at D1 is greater than 90 degrees, that's just a contradiction. We have a quadrilateral with an angle sum more than 360 degrees. So case 1 is impossible. Okay, case 1 is impossible. We arrive at a contradiction. So let's look at case 2. Okay, case 2, and now we're assuming that AD, excuse me, that AB is equal to DC, right? And then the angle at D2 there is equal to the angle at A. They're both equal to 90 degrees, which is a contradiction. Why? By theorem 7, angle D must be acute, right? So it can't be a right angle because it must be acute. And then case 3, since both cases 1 and 2 are impossible, then by the trichotomy, we must have AB is less than DC, right? So we do have that this line segment AB is less than the measure of this line segment DC, and the result goes through. Okay, so let's jump back to the PowerPoint and get rid of these lines. Why? Well, okay, this was the most complicated proof, and I don't know that this is enough for you to remember how to prove it, but we do contradiction with cases, and we have this trichotomy. You may need to remind yourself of what that is. We use theorem 7 repeatedly, and we also needed this Skew Saccheri lemma. Okay, so these are all proofs, and again, I think you can see how we're playing around really close to the rectangle place, but we don't get there. And sadly, Lambert and Saccheri, they pushed as far as they could, but they could not get us all the way to a rectangle. Why? Well, because we have this parallelism problem. Um, and it turns out that the theorems of neutral geometry can lead either to hyperbolic geometry or to Euclidean geometry. And the only way we're going to sort it out is to have a parallel postulate. Euclid's fifth is not a theorem, it is an axiom, and it has to be. Otherwise, we don't have Euclidean geometry.